A Scottish scientist walks into his laboratory on a September morning in 1928. He has been away on holiday. He notices that one of his bacterial culture plates has been contaminated, a common and usually annoying occurrence. A mold has grown on the plate, and around the mold, the bacteria are dead. He looks more carefully. He picks up the plate, he studies it, and in that moment of accidental observation, Alexander Fleming discovers penicillin, the drug that would save 200 million lives. It is one of the great stories of accidental discovery in the history of science. It is also, like most great stories, significantly incomplete. Fleming did discover penicillin. He did notice correctly that the mold was producing something that killed bacteria. He published his observation in 1929. And then, for more than 10 years, almost nothing happened. The drug that would save 200 million lives was discovered in 1928 and did not save a single life until 1941. The gap between those two dates is the real story of penicillin. It is the story of two scientists, an Australian pathologist named Howard Florey and a German refugee biochemist named Ernst Chain, who took Fleming's forgotten paper, spent years working out how to purify and produce the drug in usable quantities, and then faced a second impossible challenge: how to manufacture it fast enough to matter. It is the story of a collaboration between Britain and America that produced one of the most consequential pharmaceutical achievements in history. And it is the story of a drug whose misuse has, slowly and with gathering momentum, been building one of the most serious medical threats of the 21st century. To understand what penicillin changed, you need to spend a moment inside the world before it. Not the ancient world, not the medieval world, the world of 1920. The world your great-grandparents lived in. In 1920, if you cut your hand badly and it became infected, you might die. Not might possibly die, not might die if you were unlucky, might die in the ordinary course of events, as a result of the infection progressing, as a result of blood poisoning, as a result of processes that medicine in 1920 could observe but could not stop. The mortality rate from bacterial infections that penetrated the bloodstream was extremely high. Doctors could drain abscesses, amputate infected limbs, support patients through fever, but they could not kill the bacteria causing the problem. Streptococcal infection, the family of bacteria that causes strep throat, scarlet fever, rheumatic fever, and countless other conditions, killed millions of people every year. Staphylococcal infection, the cause of most wound infections, pneumonia, and blood poisoning, was equally lethal. Meningitis, gonorrhea, syphilis, typhoid fever, diphtheria. Each of these bacterial diseases claimed enormous numbers of lives in the era before effective treatment. Childbirth was dangerous not just because of the physical process, but because of the infections that followed it. Puerperal fever, infection of the uterus after delivery, had been killing new mothers since the beginning of recorded medicine. In the 1840s, a Hungarian physician named Ignaz Semmelweis had shown that it was transmitted by doctors who went from performing autopsies to delivering babies without washing their hands. He was ridiculed and died in a mental institution. The deaths continued. Surgery was similarly dangerous. The operation might succeed. The infection that followed it might not be survivable. Before antibiotics, the greatest risk in surgery was not the procedure, but the aftermath. The bacteria that entered the wound colonized the tissue and overwhelmed the body's defenses. World War I had demonstrated this with terrible clarity. The wounds themselves were not always immediately fatal, but the infections that followed them killed men who had survived the initial injury, killed them slowly in hospital beds from bacteria that no available treatment could reliably stop. This was the world that penicillin entered. Alexander Fleming was born in 1881 in Ayrshire, Scotland, one of 7 children of a farmer. He trained as a doctor, served in World War I as a captain in the Army Medical Corps, and returned from the war with a direct experience of the gap between what medicine could offer and what infected wounds required. He worked at St. Mary's Hospital in London in the laboratory of Almroth Wright, a prominent immunologist and a believer in vaccines rather than chemical treatments for infection. Fleming shared his mentor's skepticism about chemical antiseptics, having observed during the war that strong antiseptics sometimes damaged the body's own immune response more than they helped. He was, by all accounts, a careful and observant scientist, not a theorist, not a model builder, an observer. He spent years looking at plates of bacterial cultures, studying what happened when one organism encountered another. He had made one significant observation before penicillin. In 1921, he had discovered lysozyme, an enzyme present in tears and mucus that could dissolve certain bacteria. It was an important discovery. It was not a usable treatment. He was 47 years old when he came back from his August holiday in 1928 and noticed the contaminated plate. The details of the discovery have been disputed, elaborated, and romanticized over the decades. What is reasonably clear is this: Fleming returned from holiday to find that one of his staphylococcal culture plates had been contaminated by a mold. Around the mold, the bacteria had been killed or prevented from growing. A clear zone of inhibition surrounded the fungal growth. This was not an unprecedented observation. Other scientists had noted that molds could inhibit bacterial growth. What Fleming did was follow up. He cultivated the mold, identified it as belonging to the Penicillium genus, and tested the substance it produced against a range of bacteria. He found that it was effective against many of the most dangerous bacterial pathogens: streptococci, staphylococci, pneumococci. He published his findings in the British Journal of Experimental Pathology in June 1929. The paper was called "On the Antibacterial Action of Cultures of a Penicillium, with special reference to their use in the isolation of B. influenzae." It described, carefully and accurately, what penicillin could do. And then, for the most part, the scientific community ignored it. The question of why Fleming's discovery was not immediately developed into a usable treatment is one that historians have debated for decades. The answer involves several factors that operated simultaneously. First, penicillin, in the form Fleming had it, was not a treatment. It was a culture fluid, a mixture of whatever the mold happened to produce, containing the active substance in very low concentration along with everything else the mold produced. To turn it into a treatment, someone would need to isolate the active compound, purify it, and produce it in quantities large enough to use therapeutically. This was a significant biochemical challenge, and it was not Fleming's expertise. Fleming himself made some attempts to isolate the active substance. He was unable to do it. The molecule was unstable. It degraded quickly under the conditions available in 1929. He concluded, incorrectly as it turned out, that penicillin would probably degrade too quickly in the body to be useful as an injection. Second, the dominant paradigm in infection treatment in the late 1920s was not small molecules, but vaccines and immunological approaches. Fleming's mentor, Almroth Wright, had built a career on the idea that the body's own immune system, properly stimulated, was the best defense against infection. The idea of finding a chemical that could kill bacteria inside the body, a magic bullet in the phrase of the era, was considered less promising by many in the field. Third, a German pharmaceutical company named Bayer had actually found a class of chemical antibacterials, the sulfonamides, in the mid-1930s. Sulfonamide drugs, marketed as Penicillin and its derivatives, were effective against several bacterial infections. The medical community's attention turned to these. Penicillin, in Fleming's 1929 paper, was a curiosity. The sulfonamides were a treatment.
And fourth,
Fleming moved on. He continued his work, continued his career, continued to mention penicillin occasionally in his lectures as an interesting biological observation. But he did not pursue it. He did not have the biochemical tools and perhaps not quite the burning conviction that this specifically was the key to push through the difficulty. The paper sat. The mold sat. The bacteria waited. For 10 years, penicillin was an interesting footnote in an obscure journal. In 1938, a team at the Sir William Dunn's School of Pathology in Oxford began reviewing the scientific literature on antibacterial substances produced by microorganisms.
the team was led
By Howard Walter Florey, an Australian-born pathologist who had come to Oxford from Adelaide via Cambridge and was now the school's director. Florey was decisive, organised, driven, and possessed of an administrator's ability to assemble and focus a group of people on a specific problem. He was not always easy to work with. He was very effective. Alongside Florey was Ernst Boris Chain, a Jewish biochemist who had fled Germany in 1933 after Hitler came to power, abandoned his PhD research, and eventually found his way to Oxford. Chain was brilliant, volatile, energetic, and deeply skilled in the chemistry of complex biological molecules. He was also perpetually in conflict with Florey about credit, about money, about the terms of their collaboration. The relationship was productive and uncomfortable in roughly equal measure. Their team also included Norman Heatley, a quiet, enormously skilled biochemist who would prove to be the essential practical engineer of the Penicillin project, the person who solved the manufacturing problems that theory alone could not address. When Chain reviewed the literature on antibacterial substances, he found Fleming's 1929 paper. He was interested. He brought it to Florey. They decided to investigate. The decision was not primarily medical. Florey and Chain were scientists interested in a biochemical problem, the nature of antibacterial substances produced by microorganisms. The therapeutic implications, while present, were not the primary driver of the initial investigation. What they found, when they began working seriously on the problem in 1939 and 1940, was something extraordinary. The molecule was unstable, yes, but it could be stabilized. The concentration could be increased. The impurities could be removed. With enough skill and effort, penicillin could be purified into something that might work as a drug. Norman Heatley's contribution to penicillin is one of the most underappreciated in the history of medicine. The Oxford team needed to grow large quantities of the Penicillium mold and extract the active compound from the culture fluid. The mold grew on the surface of a liquid medium. It was a surface culture organism, which meant that to scale up production, you needed more surface area, not just more volume. Heatley, working with whatever vessels he could find or improvise, developed a system for growing the mold in bedpans, food tins, biscuit tins, hospital trays, any shallow container that could hold the culture fluid and allow the mold to grow on top. The liquid was then siphoned off, and the penicillin extracted from it through a sequence of chemical steps that Heatley refined over months of trial and error. The process was slow, the yield was tiny, and every step was difficult. Producing enough penicillin to test in a mouse required weeks of effort from multiple people. The Oxford team calculated that to treat a single human patient would require a quantity of penicillin that would take months to produce at their current rate. This was the second impossible problem. The first had been isolating the compound, the second was making enough of it. But they had enough for mice, and mice would have to do for now. On the 25th of May, 1940, Howard Florey conducted an experiment that he later described as one of the most exciting of his scientific life. 8 mice were infected with lethal doses of streptococci, bacteria that, in the quantities given, would kill an untreated mouse within 16 to 20 hours. 4 of the mice were given penicillin injections at 2-hour intervals over the following hours. 4 were not. By the following morning, the 4 untreated mice were dead.
The 4 treated mice
Were alive. Florey observed this result and understood immediately what it meant. He later said he had not allowed himself to think too hard about the implications before the experiment, for fear of what it would mean if it failed. Now, it had not failed. He walked home in the early morning light and told his wife that they might have found something very important. He understood clearly the distance between success in a mouse and success in a human being. Mice and men were different. A dose that worked in a mouse might do nothing in a person. A substance tolerated by a mouse might be toxic to a human. The work was not done, but the principle was proved. Penicillin could eliminate a lethal bacterial infection in a living animal. The molecule worked in a body, not just in a culture dish. Fleming's concern that it would degrade too quickly to be useful had been proven wrong. Chain was exultant. Heatley was quietly satisfied. Florey began planning the next step. They needed to try it in a human being. Albert Alexander was a 43-year-old police constable from Oxford. He had developed a severe infection from a small scratch, possibly from a rose thorn. The infection had spread to his face, then to his scalp, then to his lungs, then to his shoulder. Both eyes had become infected. One had been removed in an attempt to stop the spread. He was dying, slowly and terribly, from the simultaneous action of staphylococci and streptococci throughout his body. By the time he came to the attention of the Oxford team in February 1941, he had been ill for 2 months, and the infection was beyond any available treatment's control. He received his first injection of penicillin on the 12th of February 1941. Within 24 hours, the improvement was visible. The fever began to fall. The infection sites showed signs of retreating. Alexander, who had been near death, began to look like a man who might survive. The team continued the injections, and they did something that would seem shocking by later standards. They collected his urine, extracted the penicillin from it, and re-administered it. The quantities they had were so small that they could not afford to waste any molecule that had passed through the patient's body intact. For 5 days, Albert Alexander improved. And then, the supply ran out. They had produced every milligram of penicillin they had. The mold was growing as fast as it could. There was no more. Without the drug, the infection returned. Within a month, Albert Alexander was dead. The team wrote up the case as a tragic partial success. The drug worked. They simply could not make enough of it. 5 subsequent patients were treated with better results, including a 14-year-old boy with streptococcal blood poisoning who recovered completely, and a policeman with a staphylococcal infection who survived what had been before penicillin, a reliably fatal condition.
The evidence was clear.
This drug saved lives. The problem was not the science. The problem was the factory. Britain in 1941 was in no condition to build a pharmaceutical factory. The country was under aerial bombardment. Resources were rationed. Industry was directed toward war production. The chemical companies that might have scaled up penicillin production were busy with other things, and the prospect of the years of investment required to build manufacturing capacity for a drug that had only been tested on a handful of patients was not immediately appealing. Florey made a decision that would prove to be one of the most consequential in the history of the project. He would take the knowledge to America. In June 1941, Florey and Heatley flew to the United States, a significant journey in wartime, carrying samples of the penicillium mold in their coat linings, the most direct possible way of transporting what they needed to share. They met with scientists at the Northern Regional Research Laboratory in Peoria, Illinois, a USDA facility focused on agricultural fermentation. The Peoria scientists were experts in growing microorganisms at scale. They were exactly the people Florey needed, and almost immediately they made progress. Two critical innovations came from Peoria. First, a researcher named Andrew Moyer discovered that adding corn steep liquor, a byproduct of corn processing that was abundant and cheap in Peoria, to the culture medium dramatically increased the mold's yield of penicillin. Production jumped tenfold. Second, the search for higher-yielding strains of penicillium led to a systematic collection effort. Researchers contacted people around the world, asking for soil samples and mold samples. The most productive strain of all came from a moldy cantaloupe melon purchased at a fruit market in Peoria. The Penicillium chrysogenum strain, isolated from that melon, became the ancestor of most commercial penicillin production. The discovery that would save millions of lives was descended from a cantaloupe in an Illinois fruit market. Science is not always glamorous. By 1943, with American pharmaceutical companies, Pfizer, Merck, Squibb, Lilly, having committed to large-scale production, penicillin was being manufactured in quantities that made widespread therapeutic use possible. By D-Day in June 1944, there was enough penicillin available to treat every infected Allied soldier who needed it. The death rate from wound infections in World War II was a fraction of what it had been in World War I. In 1945, Alexander Fleming, Howard Florey, and Ernst Chain shared the Nobel Prize in Physiology or Medicine for the discovery and development of penicillin. Three men: Norman Heatley, who had designed the extraction process, built the production system from bedpans and biscuit tins, traveled to America with Florey to share the knowledge, and spent the war years refining the manufacturing process, did not receive the Nobel Prize. He was, by the consensus of most historians who have studied the project, as essential to the development of penicillin as any of the three who did receive it. In 1990, 45 years after the Nobel was awarded, the University of Oxford gave Heatley an honorary doctorate in medicine, the first time in Oxford's 800-year history that such an honor had been conferred on anyone. The citation described his contribution as one without which Florey and Chain could not have developed penicillin as a medicine. He was 80 years old when he received it. Dorothy Hodgkin, a British crystallographer who would later win the Nobel Prize in Chemistry for other work, determined the precise chemical structure of penicillin using X-ray crystallography in 1945. Her determination of the structure was a scientific achievement of considerable difficulty and importance. It was essential to the subsequent industrial optimization of penicillin production and to the development of later antibiotics. She received the Nobel Prize in Chemistry in 1964 for vitamin B12, not penicillin. Her work on penicillin is often overshadowed by the Fleming-Florey chain narrative. Andrew Moyer, whose discovery of corn-steep liquor dramatically increased production, received an American patent for the improved fermentation process. Florey and Heatley, believing that patenting a medical discovery was ethically inappropriate, had not patented their own contributions. This decision meant that British scientists received no financial return from the enormous American pharmaceutical investment in penicillin production, while Moyer's American patent generated significant income. Fleming himself, in the aftermath of the Nobel Prize, became a global celebrity of a kind that surprised everyone, including him. He traveled the world. He was awarded dozens of honorary degrees. Streets were named after him. He was received by the Pope. He was honored in countries across Europe, Latin America, and Asia. He accepted all of this with modest good grace. He also, to his credit, was consistently clear in public about the contributions of Florey and Chain, insisting that they deserved equal recognition for what they had done.
He was not always listened to.
The legend of the Scottish scientist and his contaminated plate was too good a story to complicate. Let me take a moment to explain what penicillin actually is and why it works. Penicillin is a molecule produced by the Penicillium mold as part of its natural biological arsenal. Molds live in soil and on organic material, in close proximity to bacteria. Many molds have evolved the ability to produce substances that kill or inhibit bacteria, substances that give the mold a competitive advantage in environments where bacteria would otherwise consume the resources the mold needs. Penicillin works by interfering with the process by which bacteria build their cell walls. Bacterial cell walls are structures that bacteria require to maintain their shape and integrity. Without them, bacteria swell and burst. Penicillin binds to specific proteins in the bacterial cell wall synthesis machinery and disables them. The bacteria can no longer build their walls. They die. This mechanism is specific to bacteria. Human cells do not have the same type of cell walls. This is why penicillin can kill bacteria at doses that are harmless to the human patient. It targets a structure that bacteria have and humans do not.
This selectivity,
the ability to kill the pathogen without harming the patient, is what makes a truly useful antibiotic. Earlier chemical treatments like arsenic compounds used against syphilis worked, but were often toxic. Penicillin was, by comparison, extraordinarily safe. The discovery also transformed the understanding of what was possible in medicine. If one molecule from one mold could do this, what else was out there? The search for other antibiotics began immediately and produced a remarkable harvest. Streptomycin, chloramphenicol, tetracycline, erythromycin. A cascade of new drugs from the 1940s through the 1960s that transformed the treatment of infectious disease. Each one followed the same fundamental principle: find a molecule that bacteria cannot live with, but humans can. The natural world, microbes that have spent billions of years competing with each other, turned out to be the world's greatest pharmacy. The effect of penicillin on World War II is difficult to overstate without sounding like hyperbole, so let me try to be specific. In World War I, before penicillin, before sulfonamides, before effective wound treatment, approximately 18% of all wounded soldiers who were admitted to hospital died of their injuries or the infections that followed them. Bacterial infections, particularly gas gangrene, tetanus, and wound sepsis, killed men who had survived the initial wounding. In World War II, with sulfonamides used from 1939 and penicillin increasingly available from 1943 onward, the mortality rate for wounded soldiers who reached hospital dropped to approximately 4%. That difference, 18% to 4%, represents, in the Allied armies alone, hundreds of thousands of lives. Men who would have died in 1917 survived in 1944 because of drugs that could stop the bacteria that killed them. The military's interest in penicillin was therefore not simply humanitarian, it was strategic. A drug that could return wounded soldiers to active duty faster, that could prevent the infections that turned light wounds into fatal ones, was a direct military asset. The American and British governments treated penicillin production as a war priority comparable to weapons manufacturing. D-Day, the Allied invasion of Normandy on June 6, 1944, was the largest amphibious military operation in history. It was also, medically speaking, the first major military operation to be conducted with an adequate supply of penicillin. The Allied Medical Corps arrived on the beaches with penicillin. The casualty rates, which would have been catastrophic in a pre-antibiotic era, were dramatically reduced. Penicillin did not win World War II, but it helped the people who were winning it survive long enough to finish the job.
On the 10th of December 1945,
Alexander Fleming stood in Stockholm to receive his Nobel Prize. In his acceptance speech, he said something that most people at the time probably heard as a polite scientific caution, and that now reads as one of the most prescient warnings in the history of medicine. He said, "The time may come when penicillin can be bought by anyone in the shops. There is the danger that the ignorant man may easily underdose himself and, by exposing his microbes to non-lethal quantities of the drug, make them resistant." He was describing antibiotic resistance. In 1945, before penicillin was widely available to the public, he was right. Bacteria evolve. They reproduce rapidly. A single bacterial cell can become a billion in 24 hours. Among those billions, mutations occur constantly. Most mutations are neutral or harmful to the bacterium, but some, very rarely, confer resistance to an antibiotic, an ability to survive in its presence. When an antibiotic is used, it kills the susceptible bacteria and leaves the resistant ones. The resistant bacteria reproduce. The population shifts. This is evolution by natural selection, happening in real time, driven by the selective pressure of the drug. Fleming warned about this in 1945. By 1950, penicillin-resistant staphylococci were widespread in British hospitals. By 1960, they were a significant clinical problem. By 1961, a strain had emerged that was resistant to methicillin, the newly developed antibiotic specifically designed to treat penicillin-resistant bacteria. That strain is what we now know as MRSA, methicillin-resistant Staphylococcus aureus. MRSA kills tens of thousands of people every year in the United States alone. Worldwide, antibiotic resistance is responsible for an estimated 1.27 million deaths per year, and that number is projected to increase substantially in the coming decades if current trends continue. The cause is exactly what Fleming warned about: overuse and misuse of antibiotics. Antibiotics prescribed for viral infections they cannot treat. Antibiotics given to livestock in low doses as growth promoters, creating vast pools of selective pressure for resistance. Antibiotics sold over the counter in countries without prescription requirements, allowing self-medication at whatever dose seems convenient.
The drug that changed death
Is now being endangered by the way it is being used. The bacteria are learning, the drugs are losing, and the world is approaching, in some estimates, a post-antibiotic era in which infections that are currently treatable will again be death sentences. Fleming saw it coming. Let me try to give a number to what penicillin and the antibiotics that followed it have meant. Since penicillin became widely available in the mid-1940s, the global average life expectancy has increased by more than 20 years. Infant mortality has fallen by roughly 60%. Conditions that were reliably fatal, streptococcal sepsis, bacterial meningitis, syphilis, gonorrhea, wound infections, became treatable. Surgical risk, which had always included the very real possibility of dying of post-operative infection, fell dramatically. Organ transplantation, which requires suppressing the immune system in ways that make the patient temporarily vulnerable to infection, became possible only because antibiotics could manage the infections that would otherwise kill the immunosuppressed recipient.
200 million lives
Is the figure most often cited. 200 million. Behind that number is one contaminated culture plate in a London laboratory in September 1928. Behind it is a meticulous Scottish bacteriologist who looked at it carefully and published his observation in an obscure journal. Behind it is a decade of silence while the paper sat unread. Behind it is an Australian pathologist who read that paper and decided it was worth pursuing. A German refugee biochemist who knew the chemistry that could make it possible. A quiet biochemist from Norfolk who built the extraction equipment from bedpans and improvised solutions to every problem the laboratory threw at him. Behind it is a cantaloupe from a market in Peoria, Illinois. Behind it is Albert Alexander, the police constable from Oxford who improved for 5 days and then died because there was not enough drug to keep him alive. Who did not die in vain because his partial recovery proved what the mice had suggested, that the drug worked in a human body. Behind it are the thousands of people who died of treatable infections in the years between Fleming's discovery and Florey's development of the drug, who might have lived if the paper had been followed up sooner, if the chemistry had been cracked earlier, if the world had moved faster.
And behind all of it
Is a mold, a small, common, unremarkable fungus that has been producing penicillin for millions of years as part of its competition with the bacteria it lives among. It did not know it was saving people, it was just trying to survive. Fleming's original contaminated culture plate, the one with the mold and the zone of inhibition around it, no longer exists. It degraded long ago, but a reconstruction of it is on display at the Alexander Fleming Laboratory Museum at St. Mary's Hospital in London. Visitors can stand in the room where the observation was made and look at a plate that represents what Fleming saw. The room is modest. A Victorian laboratory bench, shelves of preserved culture plates, a microscope. The equipment of a working scientist in a working hospital, not the gleaming apparatus of mythology. Fleming worked here for most of his career. He did important work here, the discovery of lysozyme, the observation of penicillin. He was not by any measure a failure. He was a careful, diligent, perceptive scientist who made observations that others eventually made use of. The story is not that Fleming was unworthy, it is that he was one of several indispensable people, and history, with its preference for single heroes and single moments, told his name and let the others fade.
Florey returned to Oxford after the war
And eventually became president of the Royal Society. He was later ennobled as Baron Florey of Adelaide, the man from Australia who had, arguably more than anyone else, turned penicillin from a laboratory curiosity into a drug. Chain remained volatile, remained brilliant, remained in conflict with the people around him, and remained enormously productive, eventually becoming director of the Institute of Microbiology at the International Health Organization in Rome. Heatley returned to Oxford, where he spent the rest of his career doing careful, excellent, unheroic scientific work, and eventually received his honorary medical degree at 80 years old. And the mold, Penicillium, grows still. In soil across the world, in the compost heaps and the leaf litter and the dark spaces under stones, the mold produces its molecule and the bacteria around it die, and the competition of microbial life continues, as it has for hundreds of millions of years, entirely indifferent to the species that noticed and published a paper and eventually figured out how to use it. The drug that changed death was not made by human beings. It was borrowed from the world that existed long before us and that will exist long after. All we did was notice it. All we did, and this is perhaps the hardest part, was learn to use it wisely. And then, in many cases, stop.